Okay, is there anything else? So if there is nothing else, we can go to the basics of plotting first, and after that, the rest of the things. Is that fine?
Yes, sir.
Yes, sir.
Okay, so the very basic plotting in
Yes, sir.
SageMath starts with two-dimensional plotting, and the command that we use for a two-dimensional plot is nothing but simply plot. So plot is the command that we use. So if we ask for plot, say x square, suppose that we are giving the command like this, not that x in SageMath is by default considered as a variable. So you don't have to define it to be a variable. X is freely available as a variable. You can use it anywhere you like without even saying that it's a variable. You just use it. So if you say plot x square, and if I press shift enter, the output is this. Can you see this output?
Yes, sir.
Yes, sir.
So within what range this has been plotted? Within -1 range this has been plotted. This is the default behavior. If you do not specify any range, Sage will automatically assume that you want the plot in the range -1. But that is not going to be the optimal plot always. Sometimes it may happen that we actually want the plot to be in some other region, but Sage plotted like that. But if you want to specifically say that you want plot in some specific region, you can mention that in which region you want this plot, something like plot x square in the range -5 5. Therefore the value of x will be in the range -5 5. See this, the value of x is chosen from -5 5, and the axis is also just made large, extended to accommodate this -5 and 5 values. So the extra parameter that we gave is the function. What function has to be plotted? It is x square. In what range of values the plot has to be performed? -5 to 5. This is the starting value of x. This is the end value of x. This is how plot command works. And we can, of course, plot sin x in the range -pi 5. So function you have to give first. After that, we have to specify the values. The plot is, you can see here, it is starting from somewhere here, -pi to pi. X is starting from -3.14 approximately. Y is approximately 3.14, and the plot is this. Okay, is the plot command clear now?
Yes, sir.
Yes, sir.
So
Yes, sir.
we can actually plot multiple functions in the same window like this. I'm just copying and pasting that plot. Suppose that we want to plot cos x also simultaneously in the same window. What we can do is we can add two plots. Plot sin x in the range -pi pi plus plot cos x in the range -pi pi. Therefore, if you are adding plots means that plot this -pi pi, plot within -pi pi the graph of sin x, and in the same graphing window, plot the graph of cos x also, and the result is this. Okay, so two graphs are now coming, but now the problem here is that it is difficult for us to identify that which graph corresponds to sin x and which graph corresponds to cos x. Therefore, there is an extra parameter that we can specify. Either we can give some label or we can give some color to distinguish these two graphs. So color equal to blue. Oh, blue is already there. So suppose I'm giving the color to be green, and see the output. See, the color is now green. So the only thing what I did is inside the plot command, just after specifying the range -pi pi, as the next parameter, I am giving color equal to, in quotes, green. So this green can be changed to many other color, say maroon or red, whatever. If I give maroon, color will be maroon. Of course, I can give even here some color equal to yellow, So the sign is appearing, the graph of sign is appearing in yellow color, and the graph of cos is appearing in the maroon color. So these are the extra things that we see. Initially, we started with just the function name. After that, we gave the range of values for x to choose from. After that, we gave a color for the line on which using which the plot is performed. So these are some parameters that we can use together with the plot function. So color is there, range we can specify. That is not enough. We have several other things like, so if this is not comfortable for us, if we want specifically name of the graph itself, that also can be done. I'm copying and pasting. I'm removing one of these. So I'm just going to give some green here and going to modify the thickness of the line to say 5. Let us see the output. Now see, the thickness has increased and thickness is now 5. And by default, thickness will be 1. And if we specify the color, the thickness also will change. This is an extra option that we can give. Of course, we can add 2 plots also in the same way. Now, there are many other options available. Thickness, and after that, we can give a title also, sin of x. Title has to be given in quotes. So sin of x is appearing, but title, the only thing is that the title is appearing on the top of the graph, and that title is not appearing close to that that graph itself. So, and okay, another thing, one more thing is, suppose that we are giving sin x square, the title actually supports LaTeX also. In model, if in dollar symbol we can specify sin x square, sin dollar sign x to 2. So if we specify that, you can see that sin x square, as in mathematics, sin x square is appearing here. So the title in plot supports LaTeX also to some extent. This is a graph of sin x square plotted in green color with thickness equal to 5. So these are some options available. There are many other options available. And if you want to see the options available in Sage for related to this plot command, the easiest way is to just type plot and put a question mark and press shift enter. So this is equivalent to asking help for plot. You can see that a lot of things are appearing. This is a documentation that is a part of the installed SageMath software. No internet is required for that. And the options are here. Plot points we can specify. There are several options, and many of them we may not use any time. And the other option, x minimum, x maximum, that we have already seen. Y minimum, y maximum. So that also can be given, is what we are saying. Detect faults, legend label. So all these things are here. So we will see one more command, legend label. That is going to be quite useful for us. Okay, let us copy the previous command where we plotted sine and cos simultaneously. So suppose that we are giving this is equal to legend label. That is one option. Legend label equal to sine I am giving, and let us see the effect of this. See, legend label, if I'm specifying here in yellow color, one line is given and sign is also given. Now, if I give here legend label equal to cos, see, sign is in yellow color, cos is in maroon color. That also appears here. Therefore, we can easily identify that what color corresponds to what graph. So this is known as legend label. So this is an extra option available in SageMath for this plot command. So the other possibilities available can be seen if you use the documentation help available in SageMath. Now, to find what are the colors available in SageMath, one may try colors. So you will see that a lot of colors are available here. Alice blue, antique white, aqua, aquamarine. So to see the list of all colors, Sage says that you need to use this command, sorted colors. The colors will be sorted alphabetically. And if you use the command sorted colors to see the list of all colors available in SageMath, color names. So you can see a huge list here, Alice blue, alphabetical order sorted. So these are the colors that we can use in the plot command. There are A huge number of colors are available here. Any of the color we want, if we want, we can use. And there is of course some other way to specify the color instead of using the color name that we will see later. So these are the basic functionalities of the Sage command, and we will see one more function. We will see one more plot function just to show you that the plot command in Sage can be sometimes misguiding and misleading. Okay, consider this. I am typing plot is equal to, I am plotting this floor function. Are you all familiar with the floor function? Do you know what this floor function is? You are familiar with the greatest integer function, right?
Yes, sir.
Yes, sir.
Greatest integer function means that if the greatest integer function of 3.4, that is going to be equal to 3. It is the greatest integer not exceeding 3. That is in a software language, that function is usually known as floor, because 3.4, the integer close to 3.4 just below that is known as floor of 3.4. So there is correspondingly another function which is ceil. That is the uh, smallest integer exceeding this x. Ceil means that floor is just below that and floor is just above that. Sorry, floor is just below that number and ceil is just above that number. These are the two functions available in SageMath. Okay, now I have just given p1 equal to plot. So then I have to type p1 show. I am plotting the floor function in the range -4 to 4. Output is this. There is a small problem that we can actually see from this graph. What is the problem here with the floor function? So what is the floor of, okay, what is floor of -4? What is the floor of -4? Greatest integer not exceeding -4. What is the floor of that? That is equal to -4 itself. But what is the floor of,
-4.
what is the floor of -3.5?
-3.
-3. -3.
You have to be careful. You have to choose the greatest integer not exceeding that number. Is -3 less than -3.5 or greater than -3.5?
-4.
Yes, floor of -3.5 is -4, because when we go to the minus side, we have to choose the number less than that. Number less than that means that number lying to the left of that, right? To the left
Yes,
of
sir.
-3.5, the greatest integer lying is -4. Therefore, the floor of -3.5 is -4, whereas the floor of 3.5 is 3. That's the difference. Okay. The floor of 3.5 is 3. The floor of -3.5 is 4. So if you look at this graph, so floor of -4 is 4. Floor of -3.5 is 4. -3.2 is 4. -3.1 is 4. -3.001. Floor of -3.001. That is also -4. But suddenly, when it reaches -3, the floor becomes equal to -3. Do you agree with that? So are you able to understand what I'm saying? The floor of all the integers in the range -4 up to -3, just before -3, that is equal to -4. And the floor of -3 suddenly becomes equal to -3 itself. Do you agree with that thing?
Yes, sir.
But in that case, so you are all familiar with the continuous functions, I guess. So a function is said to be continuous if there is no gap in the values. Okay, the values of f of x are very close. That is what we usually mean by saying that the function is continuous. But here, in this case, the floor function, the problem is that from -4 up to -3, just before -3, the value of floor function is equal to -4. But suddenly at -3, the value of floor function becomes equal to -3. Is this function a continuous function? Floor function or greatest integer function, is that a continuous function? So what do you think? Is that a continuous function?
It's continuous function.
Why is it continuous? What do you say that it's
Because there
continuous?
is
Don't look at the plot. I am asking something else. I am not asking for looking at the plot and answer, but I am asking that according to your opinion, without looking at the graph, see the values of, see, you can see that in the plot, you can actually see here that -4, from -4, I am moving. Are you able to follow my mouse? Are you able to see my mouse?
Yes, sir.
So from -4 to -3, what happens is the value of the function is -4, -4, -4, -4, -4, etc. up to here, right?
Yes.
But suddenly at -3, what happens is it becomes, the value becomes -3. Then it keeps again hanging on this -3, etc. -3 up to -2. Agree?
Yes, sir.
yes, sir.
But what is this vertical line?
Yes.
The vertical line means that the function is choosing the value -3.5 also. See, if you draw a line from this part of the graph to y-axis, you will see that the graph is having a value equal to -3.5, isn't it?
Yes, sir.
See, if you draw a
Yes,
line
yes.
from here, it means that there is a value corresponding to -3.5, there is a value corresponding to -3.1, but this is the greatest integer function. Therefore, there cannot be any such value. All values are integer values. So that means
Okay.
that this vertical line is not actually, that should not have been actually there. That is a mistake. Okay,
Okay, sir.
because
Okay,
the
sir.
the floor function is a discontinuous function, and therefore, if you plot the graph, it has to be just this line, and after that, suddenly the vertical line is not there. This line suddenly, and this vertical line is not there. This line. So it is a kind of step function. The values are increasing in steps. So for from -4 to -3, it is having value equal to -4. After that, it's having value equal to -3. After that, it's having value equal to -2. So it keeps on jumping. There is no connection in between. -4 to -3, in between, there is no value for the function. -3 to -2, there is no value for the function. Therefore, this function is a discontinuous function, but the plot function is showing the graph in such a way that it is a continuous function, right?
Yes, sir.
This is a mistake. Therefore, wherever there is a discontinuity, this is happening because at -3, a greatest integer function
Yes,
is
sir.
discontinuous at all integer points. So at -3 also there is a discontinuity. At -2 there is a discontinuity. At -1 there is a discontinuity. But Sage or plot function is unable to understand that there is a discontinuity. It thinks that the function is continuous and connects the points. Whatever point it is getting, it connects. So it is connecting the points, and that's why we are not seeing any break in that. So whenever you use a software for plotting, you will never see any break in that function. Even if you're plotting a discontinuous function, even if you're plotting a function where at a single point there is a break, that software will fail to show that there is a break. In most of the mathematical software, it is like that. Therefore, Sage is not an exception. It is not a problem with Sage alone. So whatever mathematical software we choose, it is going to give such a graph only. So how to avoid this problem then in that case? So we are having some problem here that Sage is doing something which, according to our mathematical wisdom, we are able to identify that this is wrong. So we have to make use of mathematics, and we have to say that this is not correct. So that is a problem. This is not correct. So we need to tell that this is not correct. But how do we tell that? We need to tell that there are certain points that needs to be excluded. That is our job. So which are the points where the problem appears? The problem appears at all the integer points. So now we are going to say that exclude points where the plot is actually discontinuous, but the plotting is done continuing that, considering that to be continuous. So the correction is the following: exclude points, exclude points. No need to include exclude points. Exclude is more than enough. Exclude. So what to exclude? minus 3 to be excluded, minus 2 to be excluded. Okay, let us see the output of this. See that? Did you see that? Minus 3, the point is
Yes,
excluded
sir.
where there is a discontinuity. Otherwise, it will connect points corresponding to minus 3 and before that. Minus 2 is excluded. So if we want to exclude all the points, minus 2 we have to exclude. Maybe we can say etc. Up to where we have to exclude, up to 4 we have to exclude. Minus 3, minus 2, etc. 4. We're plotting. See that. This is the graph of the floor function. The previously shown one is not the correct graph because the SageMath software is assuming that the function is continuous and therefore it is connecting all the points in one curve or one curved line, piece of lines. That is not actually correct. Therefore, we need to determine the points where the discontinuity is happening and we need to tell SageMath to exclude them. There is no other way. Okay. So is this example fine? If there is any question, you may please ask.
So,
Yes.
is there any way in Sage through which we can find if a function is continuous or discontinuous?
Yes, there is a way, but of course, the problem is that there are many mathematical situations, many mathematical questions in where mathematicians themselves may not be able to quickly say whether a function is continuous or not. So that is not going to be a perfect solution. That asking Sage to determine if it's continuous or not. But of course, we are going to see that how to check the continuity. We will see, but the method that we are going to suggest may not work always. Many times it is going to be successful, but I don't think that there is any mathematical software which can handle all the functions, whatever functions given, and say that this function is going to be continuous or discontinuous. But we can of course write some code in SageMath which will, to some extent, it will say that whether the function is continuous or not. That we can definitely do. You will see that.
Oh, okay, so okay.
Okay, there is one. Was that Anjana or somebody else asked? There is a question from Anjana, and the question is that at specific integer floor function is not continuous. That is correct. At any integer, no, not a single integer, the floor function is continuous. The floor function is discontinuous at every integer, and similarly, the Sage function is also discontinuous at every integer. So you need to be really careful while you are plotting. You have to take care yourself. Personal care needs to be taken in finding out if Sage is doing something wrong. See, this is one way of saying that you should not trust any software blindly. You should apply your own intelligence and see whether whatever it's doing is correct or not. And software should be taken just for supporting you. Software should not be taken for should not be considered as a decision maker. You may use the software, but the final decision about if the solution is correct or not must be yours. You cannot depend Sage or any other software blindly. That you cannot do. This is actually a model for that. Okay, so we are proceeding further. If there is no other question, we are proceeding. Now, okay, what is the next thing that we should? Uh, legend we have seen, color we have seen. There is another. We are now trying to understand the options available in two-dimensional plotting. There is a circle function available in SageMath which will allow us to plot circles given the center and radius. The function is very simple. You can expect that for drawing a circle, what are the most important parameters that we have to feed? We have to definitely give the center of that circle and we have to specify the radius also. So usually in SageMath, we will not plot immediately, but instead we will save the plot into some variable, say p. And after saving the plot into variable p, we will ask SageMath to show the plot finally. That is the common technique used in SageMath. So p equal to circle. So what is the center? 1, 2. Suppose I'm giving 1, 2. And suppose radius I'm choosing to be equal to 2. So if I am doing like this, I need to maybe I can again so I'm going to add another cycle. Okay, before that I will just see, not print. So if it is a plot, we need to show it. p dot show. That is a command. Now we got a circle here. Where is the center? Center seems to be what is the center that we gave? 1, 2. Center is at 1, 2, and radius is 2. Now, if you want to change the color, we can change the color also. Color equal to black. It's appearing. Thickness equal to all the commands that we previously used will work in the circle command here. That is fine. Line style, I think that is the command. Dotted. See, that is another command. Line style. Dotted is there. I think dashed is there. These are two extra parameters that we can give together with the plot or circle, whatever. So this is one. And now, so I can add one more circle, p plus equal to. So this means that add one more plot to the circle. 1, 3, and radius 1.5. Color, what color I should give? Red, maybe. Thickness is 4. Style is dotted. Oh, I didn't ask for showing. Okay. P dot show. So see, by putting this plus equal to, what we mean is to the previous p add one more plot. P plus equal to means that whatever was available in p, add whatever plot is available on the right to this p, and keep everything together. That is what's meant by saying p plus equal to. P show, it's appearing like this. So red colored dotted plot with center at 1, 3, radius equal to 1.5. This is how we plot circle, and of course there are many other functions available in Sage for plotting. We will not be seeing all these things, but we will be seeing the most important ones. So circle is here. Now there is one more interesting command, that is polygon. We can plot polygons also. So for plotting a triangle and etc., we can use this polygon command. P equal to polygon. In the polygon command, we need to specify the points from where to where the connection has to be made. So polygon, suppose that I'm giving from 0, 0 to 0, 1 to 1, 2, and p dot show, that will give polygon list of points I need to specify. So enclose everything within one bracket. So the polygon is here. It's a triangle. Polygon by default it is filled. Otherwise we should say fill equal to false. If you say fill equal to false, it won't be filled, but otherwise it will be completely filled. I think fill color is the command that we have to use. Fill color equal to say green, and fill equal to true. Oh, that is not working. So maybe edge color, fill, legend color. What is the color that I should use? Edge color is there. Fill is there. RGB color. Is there any other option? Edge color. There is edge color. Whether or not to fill, hue, legend color, legend label, RGB color. Where should I give the color then? Maybe can I give color itself? Let us see. Yeah, color. There is no fill color. Otherwise, edge color, there is an option. Edge color. Edge color is equal to red. See, these are the options available with plotting a polygon. See, we can give any number of points here. If you want to plot a rectangle, the coordinates we need to specify, the endpoints we need to specify, and we can plot a rectangle using this polygon command. Any number of points can be given here, and the points will be connected in the following order: first point to second point, to third point. So you need to be really careful about that, because if you alter the order of points that you are giving, you may get something unexpected. That is also quite possible. So SageMath will connect points from the beginning to end and fill all these points, fill the region inside this point using some color. That is the only thing it will do in case of polygon. So you need to be really careful about how you are giving the points inside this polygon command. This is you can plot polygon, triangle you can plot, or rectangle. So anything can plot, provided that you know the corners or vertices. If you know, then you can plot using this. And maybe I will show something interesting. This is just for fun. I'm just copying and pasting something available with me. So I'm doing this. Let us see the output. Ah, are you able to understand what I exactly did? If somebody can come forward and tell what I exactly did, then it's a great thing. So what I did here, from this code you can read and understand.
It's
Call.
infinite circle.
Infinite circles are not definitely there, because you can see that see a circle I0. Okay, so center is I and 0. So center is always at I0. What is meant by that? Center is always at I0. So initially the center is going to be for I in range 10, 9, 10, 9.9, 9.8, 9. See, here I'm keeping on varying. I'm starting with I equal to 10. So what will be the first circle then? Initially I is 10. What is the first circle?
10, 0 will be the
10,
center.
0 is the center, and radius is
10.
10. So center is at 10, 0, and radius is 10. Therefore, from 10, 0 to 20 it will go, and from 10, 0 to 0 it will go. Okay, that is the radius. From 10, 0 to 20, and from 10, 0 to the left side up to 0. Radius is 10. Okay. So the first circle is plotted with the center at 10, 0, radius equal to 10. And hue means that this is a command for giving color. So instead of saying color equal to blue, color equal to gray, I am giving something called as something known as hue, H-U-E. That is another parameter available in Sage for providing color. And hue is it's going to be a number in the range somewhere. It's going to be a number basically. So I applied a sign there basically, because if I just give one, suppose that I'm giving just one instead of hue equal to one. Hue equal to just one, suppose. Now what happened? Hue is now 1. What happened?
All circles are with same color.
All circles are with the color for which the hue corresponds to 1. Now suppose that hue is equal to I. See that? So color is getting changed, but there are only finitely many colors. Okay, but if I give hue equal to 1.5 to the power I. So anything I can give here. I want the color to change. That's the only thing. See that? U equal to, I cannot give 1 by I. The problem with 1 by I is that 1 by 0 will be appearing here. So I'm not giving that 1 by I. But instead of that, I can give e raised to I, or 1 by e raised to I. See this. You can see some rainbow effect towards the when the circles are very small, and when the circle is very large, you are seeing only reds. Okay. See here, sum circle means that plot all the circles and take the sum of all the circles. So taking sum of all circles simply means that plot all the circles in the same graphing window. That's the only meaning of taking sum of circles. Otherwise, we cannot sum in a circle. So summing here means that previously also we use the sum. You see that here we used p plus is equal to. That means that we are adding circle 1, 2, and we are adding circle 1, 3. So sum of two circles simply means that we are plotting both the circles in the same window. That is the only meaning of summing two graphs. So hue is a method for specifying color, but the good thing with hue is that hue is a number. Since hue is a number, you can keep it as a variable so that the color can be changed, and you need not worry about what color is appearing there. Different colors will be appearing here, and any function you can give here that will evaluate into a number. So this is actually a very good example of getting something beautiful in SageMath using the plot functions in SageMath. If there is any question, you may ask. Otherwise, okay, I think there is nothing, and so we will proceed now. Okay, what should I next take? Circle and okay, the other one available here. There are many other functions like ellipse is available here for plotting. Ellipse is available for plotting, and if you want to see the help, you can just type ellipse and put a question mark, and you will see that ellipse with center we have to specify, radius 1 we have to specify, and radius 2 also we have to specify, and one angle also. So let us see what exactly I meant by that. I'm just copying that. Star options, these are all optionals. So ellipse center, suppose we give center equal to 0, 0, and by R1, R2 we mean the two axes. Suppose we are giving it to be equal to 1 and we are giving it to be equal to 2, and angle means that it's rotated by what angle. So angle equal to is not necessary there, probably we can just skip that. So plotting, so we got 1, 2, 0. Okay, 1 to the right side, which is A, 2 to the upside, which is B, 0 is the center. If we give an angle here, which is probably in radians, it rotated by pi by 2. So if you give pi by 4, ellipse is rotated by pi by 4 radians. So the command for plotting ellipse is ellipse, inside that specify the center, then major axis, minor axis, or A and B, then specify the angle by which the ellipse needs to be rotated. So these are the options available for plotting ellipse. Of course, the thickness, line style, color, everything will work here. Now, one more interesting um, plot command is there. That is known as line. Line from, okay, let us give a line from 0, 0 to 1, 1. Let's see how does that look. So this is the command for plotting a line 0, 0 to 1, 1. And now, of course, after that you can specify. See the points of this end, the starting point, that initial point and end point you have to specify as list. List means that square bracket and the numbers are separated by comma inside that. But these 2 points are again to be enclosed in another list. This is the command for plotting a line. Now there is one more which is known as arrow. This is quite useful for sometimes plotting these vectors. So arrow also we are using the same command exactly. So I will copy paste same structure, only that the word is different. Okay, what is happening? Arrow from 0, 0 to 1, 1. Okay, so what is the error? Okay, let us see the help for arrow. Okay, we need to specify not as a list, but in single bracket we need to specify. So the structure is slightly different here. So instead of this arrow, maybe this is just enough. the extra bracket is not required. Let's see. Okay, the extra bracket here is not required, and even here I think then the extra bracket may not be necessary. Let's see even this. No, here that extra square bracket is necessary. Then only the line command will work. But in this case, the extra square bracket is not necessary, and it is plotting an arrow. Now we can control the width of the line, style of the line, etc. using the previous parameters. Line style equal to dotted. So dotted arrow will be there. So this is the command for plotting, and there is another command for plotting one single dot, which is the point. So only one parameter is required here. 1 1. Plot the point 1 1. So we can see that the point is appearing here. So to increase the size of the point, we may specify a size also. Say size equal to 5. Not much difference. 20. Okay, it's becoming large. Maybe color also. Black colored point. Okay, that's there. Now, if you want to plot an arrow and a point simultaneously, we can do something like this. So the arrow is pointing from 0 0 to 1 1. See this. Now we are pointing from the origin to this point. So this is the way in which we are plotting some point, and there is one more thing available. There is one more thing available, text. So the text command is used for placing some text in the graph at some xy coordinate. So if you want to specify some text somewhere, we can specifically say that I want to place the text. For example, in this example, we will see that home p equal to, because we need to plot the text also. Going to the end, p equal to p plus equal to, I am going to type some text. Point, what is the point? 1 1. But where do I want to place that point? Somewhere near, not at 1 1, because if it's coming at 1 1 itself, it will be over that text, maybe slightly below that. So slightly below that means maybe x coordinate 0.8 and y coordinate 1. And now p show. Oh, what did I do? Y coordinate 1. I actually wanted the other way. I wanted this to be 1 and this to be 0.8. So it's slightly below, maybe 0.95. Okay, 0.11. So we can not only draw an arrow, we can plot a point, and we can mark that point also. All these things can be done in SageMath using this text command. And now, if you want to plot a disk, so there is a disk option also available. Disk. So if you have some idea about the command, then you can actually ask the help about disk. And if you want to plot some disk, the way to plot a disk is this. I'm just copying and pasting to avoid some typing. So disk command needs to be used this. So disk with center at say 0 0, enter at 0 0, radius equal to 1, and we will see what this pi 3 pi by 2 means. We will see that now. So what is this? Can somebody guess what exactly happened here? Maybe I will just modify it slightly. 0 pi by 4. Now tell me what exactly happened here. Oh, pi by 42, sorry, pi by 4. What is it?
Shade the region from 0 to pi by 4.
This is actually part of the circular region. It's a part
The
of the
ray,
yeah. It's a part of the circular region, and circular region between the rays x is equal to theta is equal to 0 and theta is equal to pi by 4, right?
Sector.
Yeah, exactly. Sector. That's what I meant. Between these angles, 0 radians and pi by 4 radians in the disk with center at 0 radius equal to 1, right? It's a portion. It's a portion. It's a sector only. That's correct. It's a part of the disk with center at 0 radius equal to 1. But the angle from 0 to pi by 4 only considered. So the rest are not filled. This is what the disk command is. So I think most of the basic things available in okay, there is something extra that is known as implicit plot. Okay, that also I will explain. But we can define functions. We can define functions like this, and we can plot even that. Plot is equal to x square plus or x cube plus 3x square minus 1, and plot f within the range -5 to 5. And if we say p equal to this, then what is wrong here? 3 star x square I should have given. So if I plot it in the range -5, 5. Oh, I didn't ask for showing. You don't show. So I can see it here. Now, how can I dot a point here where this is crossing, this line is crossing the x-axis? Because I know that wherever this graph is crossing the x-axis, that point is actually a root of this function. Can I plot a point at the place where this f of x is crossing the x-axis and say that what exactly is the point? That's also possible, but we need to know how to solve equations using SageMath. But that we will do later. Now we will go to something else, and something else is to plot a circle or to plot an equation. There is an alternate way. To that we will move, and after that we will come back to solving equations. I think that is scheduled as the last session of this lecture series, right? Solving equations.
Yes, sir.
So we will not do that right now, because if you do that, it will take more time. So we will go to some other plotting. See, suppose that we want to plot. Sometimes it happens that we want to plot an ellipse. We have seen how to plot this circle, but we may not actually know what exactly is the center, what exactly A and B. But instead, we may know the equation of the ellipse. Okay, we know the equation of the ellipse, we want to plot that. But in that case, we cannot use the ellipse command, because the ellipse command actually requires that we need to clearly mention what exactly is the center, what is the major axis, what is the minor axis, what is the degree, etc. But sometimes we will be having only the equation of the ellipse. We don't have these parameters in our hand, and we don't have to solve that also. So in that case, we need to use something known as implicit plot. Implicit plot. X square by 4 plus y square by 9 equal to 1. Within the x range, here I have to specify x and y separately. Within the x range, what is the maximum value of x here? -2, 2, I guess. -2, 2. Within the y range, y -3, 3. So implicit plot. Okay, now we have to take care of some special feature of SageMath. Here, we have been continuously using the symbol x without mentioning what exactly x is. That is because SageMath by default assumes that x is a variable that's freely available to you. But if you are using some other variable name, you need to clearly mention that that's a variable. So use the command var y. Y is a variable or symbol. But it is always better to even declare x also to be a variable, to declare x also to be a variable, even though Sage understands by default that it's a variable, use var xy, var x space y, not x y, x space y. Okay, the plot is here. So implicit plot, x square by 4 plus y square by 9. Not that this is not single equal to, this is double equal to. Because in SageMath, single equal to means that you are assigning the value from right to left. So x equal to 1 in SageMath will mean you are going to put the value 1 to the variable x. But x equal to 1 means you are asking the question if the value in x is actually 1 or not. So equal to and double equal to are different. If you want to check equality, use double equal to. If you want to apply supply value to a variable, use single equal to. So this is the plot of the ellipse x squared by 4 plus y squared by 9 is equal to 1. But instead of that, we can again modify it. We can modify this. Other complicated plot also can be given. X minus 2 the whole square plus the center will be changing now. Y minus 3 the whole square by 9 equal to 1. But we are getting only a part of the ellipse because it's going somewhere. So we need to adjust this x and y. Maybe we will give, it is not going to the minus side too much. So minus 2 itself is enough here. Minus 10 or 10 we can give. Even here, I think it is better to give up to 10. So let's see. Yeah. So the ellipse is at somewhere else. And if you want to show the point also where the, we don't know exactly where the center is. Yeah, but we know what is the center of this ellipse? Where is the center of this ellipse? What is the center of this ellipse?
2, 3. 2, 3.
2,
3.
3.
0.23.
Okay. Right, you are seeing the point there, right? The center is now visible here. 0.23, that is the center. So we can plot ellipse like this, and we can plot, of course, any other, we can plot parabola here using this implicit plot. So suppose that I give y square equal to 4x, and within the range, x in the range minus 5, 5. Of course, for whatever x, y square, I can say y square equal to, I have to give double equal to 4x will not work, 4 star x I should use. So whatever value of y we are giving, we are getting x to be positive. Therefore, it is better to just keep 0, 5 here, and y say minus 5, 5. We will see what happens now. So the plot is here. So implicit plot, y square equal to 4x. The parabola y square equal to 4x is plotted. So if you want minus 4x, what happened? Maybe there are y minus 5, 5. Okay, we need to give some negative values also over minus 5. Yeah, it's coming to the minus 4 side. So this is how we plot functions using equations. So the plot command can be used if the function is explicitly non. See here the function is explicitly non. F of x is equal to x cube plus 3x square minus 1. But in this case, we don't have the function explicitly non, because from x minus 2 the whole square by 2, x minus 2 the whole square by 4 plus y minus 3 the whole square by 9 equal to 1. If you have to use the plot command, we need to find the value of, we need to write the function like y equal to something. But from this equation, finding y equal to something is difficult. Therefore, implicit plot is the function that we have to use here. So the function we have to use is known as implicit plot. And the other parameters like the thickness of the curve, line style, etc. All these things will work even here. So this is how we plot implicit plotting. Now, three-dimensional plotting is also available in Sage. So for that, instead of plot, we have to use plot 3D. Okay, f of x equal to x square plus y square. So two variables are there, therefore we require three-dimensional space. Plot 3D f of x. X within the range, what range we should choose? X in, suppose I'm giving -2, 2. Suppose y also we are giving -2, 2, and plotting. Maybe I will increase the value of -2 and 2 further. X square plus y square. Therefore, whatever x and y I choose, z is going to be okay. Maybe I can increase it to say 4, -4, 4 to get a better understanding. 4. What is this? Any idea? Any idea about this?
Ellipse.
Ellipse. This is three-dimensional. You're seeing it in the three dimension. See, if you look at this, this is actually the graph of z equal to x square plus y square, right? Z equal to x square plus y square. So if you keep y equal to 0, you will get z equal to x square. So z equal to x square, that's a parabola. If you keep x equal to 0, you will get z equal to y square. That's also a parabola. So in the when y equal to 0, you know that it's in the xz plane. So xz plane cross section is a parabola. YZ plane cross section is a parabola. Now, if z equal to 0 or z equal to some fixed number, suppose z equal to 3, z equal to 4, then x square plus y square is equal to 4, which is a circle. So at 4 height or at z equal to 4 plane, this is a circle. So what is it? So you have two cross sections parabola and one cross section circle. What is it called? Paraboloid, right?
Paraboloid.
Maybe I think circular paraboloid if you want to call it, because the circle is also, see, in the cross sections are circle and parabolas. So mainly but parabolas, because two cross sections are parabolas and only one cross section, only the z cross section is going to be a circle. Okay, when z equal to 0, it is x square plus y square equal to 0. Therefore, x and y are both going to be equal to 0. That is a single point. That is a single point appearing here. And when z equal to, okay, this is how, this is a three-dimensional object. You can, using the mouse, you can rotate it, you can see it in either direction, anything is possible. So this is how we plot functions in three dimension. If you have f of x is equal to, or, and in fact, I forgot to mention that f of x y, okay, what happens f of x? F of x y, now y is also changing. So f of x y is this now. Now, if we change it to f of x minus, so what is it now? Just like in the previous case, we can interpret f of x equal to x square minus y square. Therefore, z equal to x square minus y square. If you remove x y square, you will get z equal to x square. That's again a parabola. If you put z equal to minus y square, that is once again a parabola. And if you have 4 equal to x square minus y square, that is not actually a circle. That's a hyperbola, right? So in one cross section, it's a hyperbola, and two other cross sections, these are parabolas. What do we call that? Hyperbolic paraboloid. What is it? I don't know exactly the name for that. Something like that. Okay. Anyway, so this is how we plot functions in two dimension. And if you want to plot just equivalent to a circle command, can somebody guess that what is the equivalent of circle in 3 dimension?
Side sphere.
Sphere, exactly. So the sphere command will help you to plot a 3 dimensional sphere in this case. And uh, for implicit, corresponding to implicit plot, there is another implicit plot 3D. So x square plus y square, say minus z square equal to 1. Suppose I'm giving this, I'm taking this function. So here I have to mention the values of the ranges of x, y, and z. So minus 2 to 2, y equal to, sorry, y in the range minus 2 to 2, same range. Z in the range minus 2 to 2. Name error, x square, y square. Now the problem comes that z, the variable, is not defined. So x and y are previously defined, therefore Sage is not complaining that. Maybe we'll define all these variables once again, x, y, z. Okay. X square plus y square minus z square equal to 1. You can say that this is constructed using x square plus y square equal to 1. That's a circle. Therefore, circles are there. X square minus z square equal to 1. Therefore, hyperbola is there. X square y square minus z square equal to 1. Therefore, hyperbola is there. Therefore, in one cross section, this is a circle, and two other cross sections, this is a hyperbola. You can say that the middle portion, if you cut like this, if you cut like this, you will get a circle. But if you cut in the vertical direction or some other direction, you will be getting hyperbolas. So this is how we plot in 3 dimension using implicit plot 3D command. I think most of the plotting commands, I think we had explained. And what else is remaining? Let me see. Okay, now we will probably move to some calculus so that some calculus problems can be done using the plotting also. This is fine. Is there any question about this plotting? If somebody wants some clarification about plotting, we will give that plotting clarifications, and after that we will proceed. If not, we'll go ahead.
Sir, can we plot without the exact?
Sorry, can we plot without?
Is it possible to plot the polygon alone without x-axis and y-axis?
You want the axis to be
The
hidden.
figure alone, axis to be.
Okay, let me just see where is that plotting. Polygon, right? You are asking about polygon.
Yes, sir. Or any figure without the axis.
Okay, I understand. Okay, so I'm going to insert a cell here. Insert cell below. So what we are getting here is width axis. Okay, let us try to put something. Okay, this is what you wanted.
Yes, sir. Yes.
So you need to say SageMath that axis equal to false, because by default axis is true. And
Okay, sir, thank
you can turn on the frame if you want. So if frames, if you want to avoid, frame is a box. I think frames, I don't know. Anyway, frame is not there. That's why probably frames option is not probably there for this. And maybe, okay, is there any other picture? I think in the implicit plot, frame is appearing. Okay, we will come down to that. Implicit plot. Yeah, here there is a frame. Let us frame equal to false. Frames equal to false. Yeah, why is it giving frame? I think it's a small letter. I think it must be small letter, not capital letter. Frames or frame. Yeah, it is small letter frame. So you can turn on access by giving access equal to true. You can turn on frames by giving frames is equal to true, and you can turn off by giving that option to be equal to false. Okay.
Okay, sir. Thank you.
Okay, then now we are moving towards some calculus. Okay, now when we start calculus, the very basic function that we use is something known as the limit function. That how to calculate limits. That is what we usually use for the basic computations in calculus. So let us first get acquainted with this limit function. And limit function is quite easy. As you can see that most of the functions that we use in SageMath is the name of that function is actually exactly the same as that what we usually do in the use in the mathematics class. For limit also the function is exactly the same. The command we have to use is just limit. Initially we will choose a simple function x square at or x square minus 1, limit at x equal to 1. So what is the value that we expect? We know that it's a continuous function, therefore limit x square minus 1 at x equal to 1 is going to be equal to 1 square minus 1, which is 0. Oh, sorry, limit x, not a limit. So the value turns out to be equal to 0. So the way in which we have to use limit, the command is quite simple, limit, and then give the uh, where exactly we have to find the limit. So there is another way to find infinite limit. That is also possible. But before that, limit sin x by x equal to 0. If you try this is equal to 1. Sage understands that sin x by x, the limit is 1. If you want to find one-sided limits, for example, limit absolute value, that's a modulus value, absolute value of x, say by x at x equal to 0. So what do you think of this limit? Absolute value of x by, this is mod x by x at x equal to 0. So what do you think of this? So this is a question in mathematics. This is not, this has nothing to do with Sage Maths. This is purely a question in mathematics, and this is about limit of modulus function by x, modulus of x by x. See, if we look at if x is positive, what is the value of modulus of x? If x is positive, anybody can answer. If x is positive, what it's equal to x itself. So modulus of x by x is equal to, if x is positive,
Positive.
no. What I'm asking is,
One.
what?
One.
Yes, exactly 1, because x is positive. Therefore, modulus of x is equal to x itself. So mod x by x is nothing but x by x. That's equal to 1. When x is negative, what is mod x?
-1.
So mod x is minus x, therefore x mod x, absolute value of x by x is going to be equal to -1. So to the left of 0, the value of the function absolute value of x by x is always -1. To the right of 0, the absolute value of the value of the function absolute value of x by x is always equal to +1. So the function absolute value of x by x behaves like a constant to the left of 0 and to the right of 0. Right? Therefore, if you try to find the limit, the problem is the limit of a constant sequence, we know that it's equal to the number itself. Therefore, limit of -1 is -1. Limit of +1 is +1. But we know that to find the limit at a point, we need the left hand limit and right hand limit to be the same. But here, in this case, we will get that to be different. One -1 and other +1. Okay, let us see. So what is the answer?
Not defined.
Undefined. So the limit of absolute value of x by x is not defined. So in this case, Sage says that this is not defined. So we may try to find the directional limit, the plus direction, that's +1. That is x plus, limit x tends to 0 plus, and minus direction. Oh, sorry, parameter is wrong. Minus direction, that is -1. Okay, so we found the limit to be one in one direction and the other in the other direction. So that is how we find. Okay, and one more thing. Suppose that we call this to be equal to C. Let us see the type of C. Type of C is a symbolic expression. C is not an integer. So to check if a limit exists or not, we need to check whether the output of the limit function is an integer or not. But here, in the case limit absolute value of x by x, Sage says that the result is stored in C. C is not a number, but instead of that, it is a symbolic expression UND. UND in Sage stands for undefined. So here we can, there was a question previously that how do we find if a function is continuous or not. So one way to check continuity is that we need to see if the value of x is that, there are the conditions that we have to verify for checking the continuity of a function f is, we need to check whether at x naught, if f of x naught exists, that is the first check that we have to perform. Second check, limit x tends to x naught f of x exists. Third check, limit x tends to x naught minus f of x naught exists. Sorry, f of x exists. Fourth check, if these two limits exist, are they the same? So these are the 4 verifications that we have to make to identify if a function is continuous or not at some point. So we need to find out or try to find out 3 values and verify whether all these values are same or not. So let us try to do that now. Okay, our function is f of x equal to, suppose that we take the floor function, which we know that it's a dangerous function. So f of x equal to floor x. So f of minus 3.5. What is f of minus 3.5? It's 4. F of 3.5, it's equal to 3. Okay, everything is perfect. Now we want to see if f of x is a continuous function at say some integer value 0, x not equal to 0. So what are the 3 conditions that we have to verify? The value of the function we have to check first. So if what we have to check, we have to find f of x naught. Suppose that value is what should we call that? A is equal to f of x naught. Suppose b equal to left limit we have to find, right limit we have to find. B is equal to f of x, or f, just f, where limit at x equal to x naught, direction is minus. Now c equal to limit f x equal to x naught, but the direction is plus. So initially we will see what are the values given by this limit function. Print a, b, c. Okay. So what are the values that we are getting? What are the values that we are getting? B is equal to limit f x equal to x naught in the negative direction. So first value is 0 because f of x naught is 0. Second value we are getting to be limit f x equal to x naught, direction minus. We have already defined x naught. Okay, therefore the value is -1. The third value we are getting to be equal to, oh, are we getting 0 here? X is equal to limit f x equal to x naught, direction. Have we defined f somewhere? Okay, f is already defined. So what is the problem here? A, B, C, f from x to x naught, direction minus, direction plus. Okay, let us print it directly instead. So what is wrong here? Let's see. X going to 0. Limit of f, but that is not correct. This is -1. This is 0. What is wrong here? A, B, have we done some mistake compared to the previous step? Limit, direction plus, direction minus. So here it is working perfectly fine. X equal to, oh, that's correct. Sorry. I got confused with this absolute value function. This is correct. Okay, that's correct. Sorry, that's the correct thing. So we want to check the limit at what point? Limit at 0, direction minus direction plus direction. So from the left direction we should get -1. Okay, we are getting -1. From the right direction we have to get +1. Sorry, not +1, 0. Okay, that's correct. Perfect. Now we will check the following. If a equal to b, that means value of the function at x naught is equal to left limit, and b equal to c, that means left limit equal to right limit. Print function is continuous. Yes, we print function discontinuous. So is this fine to all of you, what we have done so far?
Yes, sir.
Okay, so let us copy everything into one input cell. Now, changing it to 1.5. Function is continuous. We will say at x naught. At x naught. Function is continuous at 1.000, etc. because it's rounded off. It's giving some extra decimal place. But if you give x equal to 1, function is discontinuous at x not equal to 1. Otherwise, function is continuous at x not equal to 1. But there is one question. I am expecting at least one of you to ask that question. So this is how we can find if a function is continuous or not, by checking the left limit, right limit, and the value of the function at that point. I am expecting some question from somebody. If you are asking that question, I will try to answer that. If you are not asking that question, I will simply skip that. Any question from anybody? So I think nobody has that question in their mind. Therefore, I don't want to give that question also, because I think if you are not asking that question, I think it's better not to go into that part. So if you are trying to do this problem, solve the continuity problem, if somehow that question appears in your mind, you may come back to me later. So for the time being, I will skip that question. I will not ask that question myself. I'm just leaving that. So this is how we check the continuity or discontinuity of a function. Left limit, right limit, value of the function. Now, going to differentiation. Differentiate sin x. with respect to x. Answer is cos x. Of course, if there is only one variable, you can even skip mentioning that variable. If there is only one variable. So differentiate sin x plus cos x. Cos x minus sin x. But if there are more than one variables, then there will be an error. Differentiate with respect to which variable we need to mention. So suppose I am mentioning that with respect to x. So this is partial differentiation. Differentiate sin x plus cos y with respect to x, because cos y is a constant according to partial differentiation. Or if I use multiplication, I will get cos y cos x. So if I want to differentiate with respect to y, I need to mention it here. This is how we differentiate once. Now differentiate sin x with respect to x and not sin x, something else, x raised to 5 with respect to x, and do it 5 times. Higher order derivative, that is 5 factorial, and it's equal to 120. So if you differentiate 4 times, you will get 120x, because last time x is becoming equal to 1. X differentiated after differentiation gives 1. Now for what else is there? So implicit differentiation is there, and okay, three-dimensional plotting, that we have already done. So limits. So what is the next thing? Maxima. Okay, we will go to some maxima, minima problems like that. But even for that, I think we require implicit differentiation. Okay, we will go to. Are you all familiar with this? What do you call Maclaurin series? Are you all familiar with that? Are you all learning this Maclaurin series, and what was the other thing other than Maclaurin series? Something else, or some other series was also there. What was that? Taylor series, right? Are you familiar with this Maclaurin series, Taylor series kind of stuff?
No, sir. Yes.
Okay, you haven't learned that, then I don't know whether it's useful to tell that thing, because if you have no idea about Maclaurin series, I don't know it's going to be very useful. Okay, let me see what. Okay, then let us see some integration stuff. So we have seen differentiation here. Now we will go to some integration also. So for integration, exactly the differentiation, of course, we can use the command like derivative is also there. So differentiation, instead of differentiation, we can use diff, not difference, derivative. Derivative of x raised to 5. So this command also can be used. DIFF and derivative both are exactly the same. Now for integration, integrate, integral or integrate sin x. Here we need to specify x as the variable. So differentiation by default it will assume the variable to be the variable in given in the function, but integration that is not exactly the same. So integration you have to mention the variable, and if you give sin x and try to integrate, it will give the answer like that. And of course, we can give the definite integral also we can find in same way. For definite integral, you need to specify 0, pi. The range we have to specify. So integrate sin x within the range 0 to pi, and the answer is this. Now, sometimes it may be necessary. We perform integration. Of course, in SageMath, you can directly feed the function and find out the integral. But sometimes it happens that we want SageMath to split the function into something useful so that we can perform integration. So one technique for splitting a function into some integrable what you call appearance is that you use partial fraction. So partial fraction, there is a built-in command for partial fraction. F of x equal to 1 by x square minus 1, say, and f of x dot partial fraction of x. That gives minus 1 by 2 x plus 1 plus 1 by 2 by 1 by 2 by minus 1 by 2 by x plus 1 means that minus 1 by 2 into 1 by x plus 1. Here it means that 1 by 2 by x minus 1 means that minus 1 by 2 into x minus 1. So for splitting a polynomial, a quotient into some degree 1 polynomial on the denominator, we can use the partial fraction function. So now to integrate multiple times for if you want to integrate, if you want to find double integral, etc., you need to integrate 2 times. There is no other way. So if you want to integrate with x, integrate with y, then you need to integrate once with respect to x. Then you need to apply the integrate command once again. It is not like the differentiation function. Differentiation function, in the bracket itself, you can specify that how many times you want to integrate. But in the case of integration, since we are integrating first with respect to one variable and second with respect to some other variable, we need to explicitly say that. For example, if you want to integrate sin x with respect to x, okay, sin x plus y, sin x plus cos y. Suppose that you want to integrate with respect to cos x. Now suppose that you want first integrate with respect to x, next integrate with respect to y, then you need to there is no other way. You need to type the command 2 times. Integrate with respect to y. There is no other way. You need to do this. Integrate. Okay. So we get the answer to be equal to minus y star cos x plus x star sin y. So this is how we perform integration, and integration is quite simple. There is nothing much that we need to use for integration. Now, what are the other things remaining in calculus? Okay. Okay, now surface of revolution. Surface of revolution, we usually take a curve and revolve that around some axis to get the surface of revolution. And surface, for finding the surface of revolution, for plotting the surface of revolution, there is a built-in command available in SageMath. Suppose that we take f of x is equal to x square. It's a parabola. F of x equal to x square. Now suppose that we want to plot it. So for plotting the surface of revolution, the command is to just use revolution plot 3D. The function f we have to plot, and within what range we have to revolve, that we need to mention. Suppose that we mention that the range of x is from, say, -2 to 2. Let us see the plot. So this is the plot of, this is the revolution, this is the surface of revolution of the curve f of x is equal to x square. Now, if you take x square, curve we have to choose definitely. So what other curve I should choose? X square plus 1. That's also the same because x square plus 1 is also going to be another parabola. So the surface of revolution we can find using the revolution plot 3D command. So this is another command available, another function available in SageMath. And after that, in plotting, I think we have covered most of the functions available in SageMath and most of the plotting functions available in SageMath. Now I think we need to. So the students, do we have final year students also available here?
Yes, sir.
So final year students, I think it will be able for it will be easy for them to understand the concept of maxima, minima, etc. Because I think in the fourth semester probably they are learning it, right? Or second semester, maxima, minima problems in differentiation.
It
Second
is in
semester.
second semester.
It is in the second semester, right?
Yes.
Yes, sir.
Okay, we will try to see some maxima minima problems. So we know that the relative maximum, relative minimum. So maximum minima comes after finding relative maximum and relative minimum. We know that relative maximum, relative minimum of a function exists at critical points, where critical points means a non-differentiable point or derivative equal to 0 points. Okay, you know that. Okay, fine.
Yes, sir.
I think since first year students are not already there, I think only second year students and final year students will be here, and they must be knowing this maxima minima. So for finding maxima and minima, we need to find out that where the function fails to show the derivative, or where the function has derivative equal to 0. And most of the times, in most of the problems that we will be facing, the function will be having derivative, but the derivative will be equal to 0. So now, what we are going to do is we are going to use we are going to solve the for the points where the derivative is 0, and we will try to find the maximum from those points. Okay, maximum or minimum for that function in a particular range. Okay, so the problem now is to find maxima and minima, and we will try to use plotting also together with that. So our problem is find maxima, minima. Okay, I'm defining a function f of x equal to x cube minus 3x. Be careful, don't type 3x. Instead of that, type 3 star x, because 3x will not work here, plus 2. So a function is defined. Now, not that we need to check, we need to see that the function is differentiable or not. Since we are using a polynomial, we don't have to worry about that. The function is anyway going to be differentiable. So once the function is differentiable, okay, let us see the plot of this function. Plot. We will call this as function plot of this function f. So f plot. Plot f in the range. Okay, what range we should plot? Maybe some randomly I'm choosing some number 3 3. Let us see the plot. Okay, the plot is appearing here, and you can now guess that the maximum, there is a local relative maxima of this function that is occurring at -1, and relative minima is, okay, where is the relative minima? There is a relative minima at 1. Are you able to understand that?
Yes, sir.
So relative maximum means that you are taking a peak, and to the left of that and to the right of that, the value of the function at that point should be more. So you can see that at this point somewhere, the function value is maximum compared to its neighborhood, and at this point somewhere near 1, the value of the function is compared to its neighborhood, it's least. So there is a maxima, there is a relative maxima, and there is a relative minima also for this function. So we need to check where this is, where the maximum is occurring, where the minimum is occurring. For that, we need to find the critical points first. We can see that This is a polynomial function. Therefore, there is no problem of non-differentiable points. There is no such point. So, critical point in this case are the points where the derivative is 0. So, we need to differentiate. We need to find the first derivative and see at what points for what values of x the derivative becomes equal to 0. Let's do that. Suppose f1 is the first derivative. Differentiate this with respect to x. Let us see that in print. F1 is 3x square minus 3. 3x square minus 3. That's correct. Okay. Now we have to solve for. Okay, we will give a decent look for the output. First derivative of f is that I am using a new command. I have not used the print like this previously. First derivative of x going to x raised to 3 minus 3x square 3x plus 2. That's a function. This is f of x. X going to x cube minus 3x square, not 3x square, x cube minus 3x plus 2. This is the function. And
Sir, your presentation is not visible, sir.
oh, just 1 second. But when did that go? Just now?
Yes, sir.
Okay, previously you were saying, right?
Yes, sir.
Oh, I don't know how did that happen. Okay, it automatically gone off. I didn't do anything, and suddenly somehow it happened. Now is it visible now? Is it visible now?
No,
No, sir.
No.
no, sir.
Oh, but it is showing that it is presenting. Okay, let me stop the presentation and let me start once again. So plotting.
Yes, now it's visible, sir.
Oh, somehow I don't know what happened in between. It automatically turned it off. But only these many things. Only the input cell where I'm currently typing, that only you couldn't see, right? Previously you were saying.
Yes, sir.
Okay. So I'm differentiating using the diff command. F1 is equal to diff f of x means that f1 is the variable where the derivative of f is stored. Now I am printing that first derivative of. See, I'm putting curly braces here and another pair of curly braces here, and inside the format command I am giving f. So this f corresponds to first curly brace. The second curly brace corresponds to f1. So f will be printed, f1 also will be printed. So first derivative of x going to x cube minus 3x plus 2 is x going to 3x square minus 3. Fine. Okay, so we found the first derivative. Now the next thing is after finding the first derivative, now we have to solve for the critical points. But how do we solve for the critical points? We need to solve the equation f1 equal to 0. So we are going to do that. So critical point equation is equal to f1 equal to 0. See, how did I do that? Critical point equation. So CPE is a variable where I am storing the equation f1 equal to 0. I am going to solve critical point equation. Are you able to understand that?
Yes, sir.
Okay, now I am going to solve. Critical points is nothing but it's equal to CPE. I have to solve it. Solve for what? Solve for x. Now let us try to print it. What are the critical points? Critical points are -1 and 1. Just look at the commands that I executed. Initially, I put the equation f1 equal to 0, that is first derivative equal to 0, into a variable called CPE. Now, I'm going to solve CPE for x. So, I am solving first derivative equal to 0, and the solutions are put inside the variable CP. So, I get x equal to -1, x equal to +1. The command I used is solve. Okay. The command I used here is solve. Fine.
Okay, sir.
Now, but here is a small problem that we are seeing. We didn't get any number here, but instead of that, we are getting inside square bracket. Square bracket is a list. X equal to -1, x equal to +1. But we are not interested in that x equal to symbol, x equal to symbol. These things we are not interested. Therefore, to get those things, we will put x1 equal to the first value, first critical value. First critical value is CP0. But what is CP0? Let us see that. Print CP0. So what will be printed here? So this is printed here. X equal to -1. But we don't want that x equal to. We want only the right side of that. So CP0 right hand side. CP0 right hand side. That is -1. So the values we want are CP0 RHS and CP1. This is CP0. Critical point 0. This is CP1. Critical point 1. So we need x1 equal to the first critical point. Only the value we require. We don't need the variable name. X2 equal to CP1 dot RHS. So these are the two critical points. Let us see that. Print x1 or critical points are, and so put it in the inside format. X1, x2, critical points are -1 and +1. Okay, this is fine up to here. This is okay up to here.
Yes, sir.
Yes, sir, it's clear.
Okay, now what do we want to establish if it's maximum or minimum? What is the next thing that we need? What is that? See, we have located critical points. Now we need to check if if second derivative of f at x naught is greater than 0, then f has a local minimum. If second derivative is less than 0, then f has a local maximum. Okay, do you agree to that? That calculus information we have. So we need to check the second derivative. Fine.
Yes, sir.
So we will check the second derivative. F2 equal to differentiate. Either we can differentiate F2 times or we can differentiate F1 one times. Anything is fine. So what is the value of if F2 of x naught? F2 is found. If F2 of x naught, not x naught, sorry, x1 is what do you have to check? If it's greater than 0, so what is the conclusion we have? If it's greater than 0, then we know that it is a local minimum. It is greater than 0, then print f has a local minimum at what point? At x1. Else what we will do? Else we will print that it has a local. We cannot do that. Else if it is greater than less than 0, f2 of x1 less than 0, we will print that f has a local maximum. Let us say that.
Sir, else, ELS.
Oh, no, else if is that wrong? No, that is, I think, okay. Let us see. If there is a bracket extra. No, there is no bracket extra. What you were saying, elif, that is correct. Else if is what we wanted. Okay, let us see the mistake here. There is some error message appearing here. Unable to make sense Maxima expression. Where is that mistake coming? Syntax error in where? Okay, there is something wrong here. Okay, let us see. F2 of x1 greater than 0. F2 of x1. F2 is already derivative. If it's greater than 0, okay, let us see if this command is correct. This is correct. Else if or elif, what is the command? Okay. Elif print f has a local. Else is not correct because it can be even equal to 0. Okay, we'll try that. Is it else if? No, that's correct only. Elif.
So there is a bracket missing in elif.
There was missing, right?
Yes, sir.
Elif
Af-
is correct now.
Less than 0.
Less than. Sorry. Okay. Good. So f has a local maximum at -1. Is that correct? Local maximum. We will see the plot.
Sir.
Oh, that's wrong, right? A local maximum at -1. Correct. Maximum at -1. That is fine. That's correct. So f has a local maximum at -1, or okay, but we have two values. We have two critical values for uh, C in. What are the two critical values? X1, X2. We will make both these checks simultaneously in a for loop, and we will push everything here to one extra tab. See that this if is inside 4, therefore one tab, but print is inside if and 4, therefore two tabs. Okay. See, if is inside 4. We want to check f2 of x1. We want to check f2 of c, not x1. C. C is initially f1, and after that it is C is initially x1, and after that is x2. Okay, now what happens? So the final answer is this: f has a local maximum at -1, f has a local minimum at 1. See if it's correct. This is correct. Local maximum at -1, local minimum
Yes,
at
sir.
1. Okay. Let us also see the plot. Plot. We will plot a point. Which point we should plot? P equal to plot f minus 3. We will add the maxima and minima to that plot. F as a local minimum. P corresponding to critical points, we will mark the points there. P plus equal to point. What is the value of x? That is C, f of C. And what is the value of? Okay, and after that we will ask P dot show. Let us see the plot also. So here point C, f of C, one bracket is missing. Invalid syntax, integer 0 if f2 c. What is the mistake here? P plus equal to point C, f of C, one more additional bracket missing. Okay. See the plot here. This is one. This is the maximum point. This is the minimum point. If you want to increase the size of this, that also can be done. Size equal to 20, color equal to red. See that we have marked the point of maxima and marked the point of local minima also. This is how we use Sage for solving maxima minima problems. And of course, using the same techniques, we can solve many other problems in Sage, like solving Lagrange's problem and all these things. Of course, if time permits, we can do all these things. But maybe in the next session, I think we have what is it? It's a linear algebra, I guess. So if we are getting some more time, we will try to solve this gradient, what you call Lagrange multiplier related problems. But the only thing is that second.